Dear friend, welcome to this lecture of inner product spaces. In this lecture, we shall see some illustrations of Gram-Schmidt orthogonalization process. In our last lecture, we have seen or we have proved a theorem of Gram-Schmidt orthogonalization process. The theorem states that if V is a finite dimensional inner product space, then this inner product space V has an orthonormal set as its basis. It has orthonormal set as its basis, of this V. That means, given any basis of V, we can construct an orthonormal set which is again a basis of V, and that means we orthogonalize the vector. Actually, the vectors will be orthonormal, each having length 1, and they are mutually orthogonal to each other. So, I have written here two problems, and we shall use the same procedure that we have used in the proof of the theorem. This theorem that V is finite dimensional inner product space, it has orthonormal set as basis. So, that proof of that theorem or that Gram-Schmidt orthogonalization process, we have used the procedure or we have used the construction, and the same construction we shall use to solve these problems. Now, the two problems I have written here, we shall solve these one by one. See, the first problem is, here the inner product space is V, which is f of F3, three-dimensional real, F is real field or field of real numbers, and therefore, this is a Euclidean space, three-dimensional Euclidean space. Define the inner product in this as if U is x1, y1, z1 and V is, see, it has three components and V has x2, y2, z2 and they belongs to V. That means this F3. Then the inner product of U and V is defined as x1, x2 plus the first component of these two vectors x1 into x2 plus product of the second components y1 into y2 plus z1 into z2. So, that is the inner product defined. Actually, it is a dot product of two vectors. We know the dot product is defined in the same way. If this vector is x1i plus y1j plus z1k and this is x2i plus y2j plus z2k, then their dot product u dot v is defined by this expression. So, we shall from this basis, and suppose this is a basis. See, to get an orthonormal set as a basis, we should first have a basis. Consider any basis, and we shall then convert that basis to orthonormal set, which is again a basis for V. So, that means given a basis or starting with this set as basis of V, F3. So, this is independent set of independent vectors which spans F3, and therefore, it is a basis from this basis. But here the vectors are not orthonormal. These are not orthonormal vectors. We shall form a set of orthonormal vectors, which is again a basis of V, using the procedure that we have used in the proof of the theorem 2. So, solution for the first example. Here S is given as this V1, V2, V3, and let S, the vectors in S we shall denote by V1, V2, V3. Then what is V1? Then V1 is 1, 0, 0, V2 is 1, 1, 0 and V3 is 1, 1, 1. These are the vectors, and we shall have to obtain from these vectors V1, V2, V3 another basis which may be denoted by S1 as W1, W2, W3. Basis contains the same number of vectors, and therefore, this must also contain 3 vectors, and but here these W1, W2, W3 are orthonormal, or this S1 is orthonormal set. Each vector must be of length 1, and we must have they are mutually orthogonal, that is the inner product of Wi Wj is 0 if I is not equal to j. So that is the condition, and we have first, that is W1 is defined as, see, we take W1 is equal to V1 divided by norm V1, V1 divided by norm V1. This is what we have the construction in the proof, and therefore W1 will be V1. What is V1 is 1 0 0, and what is norm V1? Norm V1 is inner product of V1 with V1, and see, inner product of V1 with V1 is, and it will be under root of, it's under root of inner product of C, this will be norm V1 is root of, by definition, inner product of V1 and V1, and therefore it will be under root of, what is by definition of inner product of V1 with V1? That means component wise multiplication and their addition. So it is 1 into 1, that is 1, plus 0 into 0 plus 0 into 0, and that is equal to root of 1, which is 1. So therefore norm of V1 is 1, and thus this vector is same as 1 0 0. This is W1, since norm V1 is 1. Next, if W1 is constructed, we shall find out what is U2. Now U2 is, by our construction, this is minus V1 into W1 multiplied by V1 plus V1. This we have in the proof. This we have considered the vector U2 as like this in the proof, and therefore we shall use that result directly here, and therefore what is U2? U2 is minus V1 and inner product of V1 and W1. So what is a V1? V1 is 1 0 0. So it is 1 0 0, and what is W1? W1 it is again 1 0 0, and multiplied by V1. So V1 is again see, it is not like this. So U2 is U2, we have not V1 but V2. V2 inner product of V2 with W1 into V2 plus V2. So we should correct it. This is the expression for U2. And now what is V2? V2 is 1 1 0. So this is 1 1 0, and W1 is the same 1 0 0. W1 is same as V1. We have obtained W1 as same as V1. So V2, this is multiplied by V2, which is 1 1 0, and plus added in this we have to add again V2, that is 1 1 0. So these expressions we have for U2, and this is equal to, now what is product of this component wise? See, this is the definition, product of U and V. X1 x2 means 1 into 1, that is 1. So it is in bracket 1 into 1 plus 1 plus 0, that is 0, 0 plus 0 is 0, and therefore it is 1 only. I have written this directly, and minus 1 multiplied by 1 1 0 plus 1 1 0, and thus see what will be this. This is minus, we have to multiply by minus 1 to each, minus 1 0, and then 1 1 0. So therefore this will become, see, the first is, this is multiplied by V2, V2 multiplied by inner product of, see, this is not V2, this is what is W1. So this is a correction again. You should see the steps in the proof. It is U2 is minus V2, inner product of V2 and W1 multiplied by W1 plus V2. Again we have to correct this. This is 1 0 0. 1 0 0, W1 is 1 0 0, and therefore this product will be, now you see 1 into 1, that is 1, 1 plus 0, this is right. So, this is 1 and only this vector is 1 0 0, and therefore, now you see this will be minus 1 0 0 plus 1 1 0, and thus u2 will be, so this vector u2 is, this is w1 we have obtained. I shall write it here. W1 is same as this one, and now u2 is, u2 we have minus 1 plus 1 is 0, 0 plus 1 is 1, component wise addition. So, that is 0, 1 and 0. So, this is u2 which is non-zero vector. What is our w2 vector now is, take w2 as, this is the, these are the values. We have some corrections here, you refer the earlier proof. This is the correct value of u2. We have calculated u2 as this, and w2 is u2 divided by norm of u2, and again we see norm of u2 is 1. It is under root of sum of squares of this, under root of 0 square plus 1 square plus 0 square, and that is again root of 1, which is 1. So, this is 1, as earlier we have seen norm of w1 is 1, and thus this is 0 1 0 divided by 1, or which is w2 is the same as 0 1 0. So, this is the vector w2 we have obtained, and I shall write it here. W2 we have obtained as 0 1 0. We are obtaining from V1, V2, V3, W1, we have obtained W1 and W2. What remains is only to find out W3. Now, we write as U3. Next, U3 is equal to, see like this, how to write U3. U3 is to be written as minus V3 product with inner product with W1 multiplied by W1 minus inner product of V3 with W2 multiplied by W2 plus V3. This is the expression for U3. Extending this in place of V2, now it is V3, inner product of V3 first with W1 multiplied by W1, etc. So, this is the expression for U3. Now, we calculate this U3. So, this is equal to, U3 is equal to minus what is V3? V3 is here 1 1 1, inner product of 1 1 1 with W1, that is 1 0 0 multiplied by 1 0 0. This is the first term, and minus, I shall write this next, V3 again is 1 1 1 and its inner product with W2. W2 we have obtained as 0 1 0 0 1 0 and multiplied by W2 again 0 1 0 plus V3. V3 is 1 1 1. We shall see these products first, and then I write here, this is U3. U3 is equal to, see negative sign, what is the product of this component wise multiplication and their sum. Sum of the component wise multiplication, 1 into 1, that is 1, plus 1 into 0, this is the definition, 1 into 0, that is 0, and 1 into 0, that is 0. So, only 1 is there, and that is minus 1 multiplied by 1 0 0, and you see this is 1 into 0, that is 0, plus 1 into 1, that is 1, plus 1 into 0, that is 0. That means again it is 1, minus 1, and multiplied by 0 1 0, and last term is plus 1 1 1. And now we will have to multiply this, we have to add this component wise. So, this is minus 1, this is minus 1, this is 0, and this is plus 1. So, minus 1 plus 1 is 0, and next this is 0, this is minus 1, and this is plus 1. So, it is 0. in the same places elements components we have to add. This is 0, third component now, 0, this is 0 and plus 1. So 0 plus 0 plus 1, that is 1, third component. So this is U3, and now we take W3 as, U3. This is in the definition we have in the proof of the theorem, we have considered W3 as U3 divided by norm U3. And you see what is U3 we have obtained. First we have obtained U3, then we have obtained W3. 0, 0, 1 divided by norm of this vector is again 1. Under root of 0 square plus 0 square plus 1 square, and that is 1. So this is 1, and therefore W3 is 0, 0, 1. Thus we have obtained W1 earlier, W2 next, and now W3. So thus these vectors, thus W1, W2, W3, and is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1 is orthonormal set, is an orthonormal set which forms the basis for this set F3, and this is actually the standard basis, is the orthonormal set. Is the orthonormal set which is the basis, which is a basis of, or which forms a basis for this F3. V is equal to F3. Vector space is F3, three-dimensional Euclidean vector space. And this we know is a standard basis, and here the vectors are each of length 1. Length of each vector is 1, and they are mutually orthogonal, pairwise orthogonal, and thus we have given this as the basis 1 0 0, 1 1 0 and 1 1 1. We have converted this, from this basis we have constructed another basis which is orthonormal set, and a basis of the same vector space. So this is the procedure we have used, that is Gram-Schmidt orthogonalization process to obtain an orthonormal set which forms a basis. So this completes the solution for the first problem. Now we consider the second one. Here f be real field again, and let V is equal to f of x, the set of polynomials in x. This is a vector space of polynomials in x, and over f of degree 2 or less than, or 2 or less means 2 or less than 2, less than or equal to 2. In V, define inner product by this. The inner product is defined like this. Px and qx is a polynomial in this vector space. Then the inner product of these two polynomials px and qx is equal to integral minus 1 to 1 px into qx into dx. So this is the definition of inner product. Obtain an orthonormal basis for V. So we shall start with solution of 2. First we have to write a basis, that is known basis for V, and you see V is a polynomial of degree less than or equal to 2. See, this is a set of polynomials in x of degree less than or equal to 2. Since V is equal to f of x is a set, or is the set of polynomials of degree less than or equal to 2. The set, we have a basis of this, we have S is equal to, basis of this we can consider as polynomial of degree less than or equal to 2, means maybe of degree 0, maybe of degree 1, maybe of degree 2, and therefore the set 1 x x square is a basis for V, forms a basis of V. Any polynomial of degree less than or equal to 2 can be written in combination of this. That is a linear span of this, linear span of 1 x and x square. So therefore this forms a basis of V is equal to f of x. But you see, this basis is not orthonormal. This basis is not orthonormal, and we shall construct a basis which is orthonormal. That means length of each vector must be 1 and the vectors must be mutually orthogonal to each other. So as earlier, we have given this basis and we have constructed orthonormal basis from the given basis. Here what is V1? We take this as V1, V2 and V3. We have V1 is 1, V2 is x and V3 is x square. First vector we shall obtain as W1. Take W1 as V1 divided by norm of V1. So that is in the proof of the theorem. And therefore this is what is V1? V1 is 1 and divided by what is norm V1? Norm V1 is under root of inner product of V1 with V1. And that means inner product, what is V1? V1 is 1. So therefore inner product of 1 with 1. Under root quantity of inner product of, by definition, norm V1 is under root of inner product of V1 with V1, V1 is 1. And here we have to use the definition. Inner product of P and Q, Px and Qx is integral minus 1 to 1 product of Px and Qx into dx. So therefore this will be 1 divided by under root of integral from minus 1 to 1, 1 into 1 into dx. P and Q are both 1 here, and therefore what is the integral of dx? The integral of dx is, so I shall write here itself, W1 is equal to 1 divided by under root of, or I can continue here, this problem we have solved, so I shall use this space to write. So what this will be, W1 is, so W1 is 1 over under root of the integral of 1 dx is x, and the limits are minus 1 to 1, and therefore this will be 1 over see the value of x as upper limit is 1, lower limit is minus 1, so 1 minus 1, that is 2, and therefore this is root 2. This is the value of W1. So W1 is 1 over root 2. Now we have to find out what is U2. Now U2 is we know it is minus V2, inner product of V2 with W1 multiplied by W1 plus V2. This is the expression for U2 that we have written in the proof of the theorem number 2, Gram-Schmidt's orthogonalization process, and we put the value of this V2 and W1. We have to obtain this first, that is inner product of what is V2. V2 is see this x, V2 is x, and what is W1? W1 is 1 upon root 2 multiplied by W1, that is 1 upon root 2 plus V2. V2 is again x, see second vector. And now we have to calculate this minus. How to calculate inner product of x and 1 by root 2? Using this definition. It is integral from minus 1 to 1 product of these two. So this is integral from minus 1 to 1 product of x and 1 by root 2 into dx. So this much is the inner product of this multiplied by 1 by root 2. I shall write this in bracket, and 1 by root 2 plus x. So further calculation gives this 1 by root 2 and 1 by root 2 are constant, and that will be 1 upon 2. Integration of x dx is x square by 2. The limits are minus 1 to 1 and plus x, and further this calculation gives u2 as, so u2 is equal to, this is half, and this 2 can also be outside the limits here this expression, so it is 1 by 4, and see, but the upper limit is 1, so it is 1 square, minus the lower limit is minus 1 minus 1 square, and they cancel. Actually this will be 1 by 4 in bracket 1 square is 1 minus 1 square is again 1 and plus x, and thus this is only x. u2 is equal to x. You can verify this and take now w2 as, take w2 as u2 divided by norm of u2. This is in the construction, in the theorem's proof. And what is the u2? u2 is x. So this is x divided by norm of u2. Norm of u2 means under root of inner product of x with x. And that is again by this definition of inner product. It will be x divided by, I now write here, this is what we have written is w1. w1 is 1 by root 2, and I write that vector here. w1 is 1 by root 2. Now this w2 we are calculating. w2 is equal to x divided by under root of inner product of x and x means integral minus 1 to 1 x square into dx, and that is x divided by under root of integral of x square is x cube by 3. The limits are minus 1 to plus 1, and that will be equal to x divided by under root of, put the upper limit as 1, so it is 1 by 3, minus put the lower limit as minus 1, minus 1 cube is minus 1, so finally that becomes plus. You should see this calculation, I shall write it directly. So it is 1 by 3 minus 1 by 3, and therefore it will be 2 by 3, and thus or that can be written as w2 is equal to this is root 3 by 2 times x. So this is the value of w2 we have, and I shall write that value here. w2 is equal to root 3 by 2 times x. Now we need the what is w3. Two vectors we have obtained. The basis contains 3 vectors, so we want w3, and for w3 we consider u3. Next u3 is u3, we know it is minus v3 inner product of v3 into w1 multiplied by w1 plus it is minus again inner product of v3 with w2 multiplied by w2 plus v3. So this is the expression for u3, and thus u3 is equal to minus what is v3. You see v3 is third vector, that is x square, inner product of x square and into with w1. What is w1? It is 1 by root 2 multiplied by 1 by root 2. Next is minus v3 is again x square. What is w2? w2 is this vector just we obtained under root of 3 by 2 into x. X is outside the root. This is the inner product of these two multiplied by w2, that is under root of 3 by 2 multiplied by x, and plus v3 means x square. So this is to be calculated, then we get u3. So u3 will be, I see, this is u3 is equal to minus, now inner product of this will be using this definition, that is minus integral from minus 1 to plus 1 product of these two, x square into root 1 by 2. So that is 1 by root 2 x square into dx. So this much is the inner product of these two multiplied by 1 by root 2. That we have written. Next minus again integral from minus 1 to 1, product of these two, that will be in product of these two will be x cube into root 3 by 2. So we can write root 3 by 2 first into x cube into dx. So this much is the inner product of this, and that is multiplied by root 3 by 2 into x, and last term is plus x square. So this is the expression for u3, and that u3 can be further calculated as minus. So integral of this, see, this is 1 by root 2 and 1 by root 2, that is 1 by 2 is constant, and integration of x square is x cube by 3. The limits are minus 1 to plus 1. So this is the first. Next is again you see this product is square root eliminates minus 3 by 2, and the integration of x power 4. This will not be in the integration because this is to be put in bracket. This is separate term, so this must be outside the integral. We have to write this as this can be written outside the integral, 3 by 2 times x. This x must be written first. Here it is all right. So here this is x square integration is x cube by 3 and this constant. So this must not be multiplied with integrand. This is inner product. This is inner product, and then it is multiplied by x. So this is first we have written the term 3 by 2x, and now the integration of x cube is x square x power 4 divided by 4, and the limits are minus 1 to plus 1 plus x square plus this term x square. You note this, and further we have to evaluate this, that is minus half. See, the upper limit is 1/3 minus again minus 1/3, that will be 2/3. This value is 2/3, check it, minus 3 by 2 times x, and this is 1 by 4 minus again 1 by 4, because minus 1 power 4 is 1, so that will be actually 0. The evaluation of this expression is 0 plus x square, and thus finally u3 will be, we write u3 here, therefore u3 is this is minus 1/3 plus x square. This is u3, and now we have to write w3. Take w3 as u3 divided by norm of u3, and that is minus 1/3 plus x square divided by its norm. Its norm means under root of inner product of minus 1/3 plus x square minus 1/3 plus x square, inner product of this, and I shall write now here as this w3. w3 is equal to, the numerator adds the same, divided by, and we have to write using this definition, under root of product integral from minus 1 to 1, product of these two, means actually it will be square of x square minus 1/3 whole square into dx, px into qx, the same term is there, so it will be square, and thus this can be further evaluated as minus 1/3 plus x square divided by under root quantity, integral from minus 1 to 1, we shall expand this, and that will be x power 4 square of x square minus the middle term is 2/3 x square, and the third term is square of minus 1/3, that is 1 by 9 into dx. So we shall evaluate the integral here, and that is minus 1/3 plus x square under root quantity of the integral values we should write x power 5 divided by 5, integral of this minus 2/3 x cube divided by 3 and plus 1 by 9 x, and the limits of this are from minus 1 to plus 1. Now we further evaluate this, and that is W3. W3 is equal to, this is minus 1/3 plus x power 2 divided by under root quantity of, you see the upper limit is 1, lower limit is minus 1. So it is 1 by 5 minus 1 by 5. So that will be 2 by 5 in the, or you can put the upper limit throughout and then lower limit throughout the expression. So upper limit is 1, means 1 by 5, it is 1 by 5 minus this is 2 by 9 and 1. So 2 by 9, and next is plus 1 by 9. This much is the upper limit, and minus the lower limit will be, put x as minus 1. So it is minus 1 by 5, and next is this is again minus 1, so it becomes plus. So yes, so minus 1 cube, that is plus, and that minus 1 and this minus and this minus sign becomes plus. So it is 2 by 9, plus 2 by 9, and last is minus 1 by 9. This is the expression. Now we see this is equal to minus 1/3 plus x square divided by under root. So we are only evaluating the definite integral, and you see this is this becomes plus 1 by 5, this becomes minus 2 by 9, this becomes plus 1 by 9. That means the expression is double of the first bracket. And what is the first bracket? 1 by 5 minus 2 by 9 plus 1 by 9, that is minus 1 by 9. So it is 1 by 5 minus 1 by 9, it is double of this, and that is 9 minus 5, that is 4 by 45. You can check it, and it will be 8 upon root 45, or that we can write this as a 5 into 9 we write as it is. So this is 4 and this is 5 into 9. So it will be 2 by 5, 4 by 9. 2 into 4 divided by, or 2 into 4 divided by 5 into 9. So why we have written like this? Because these are perfect squares and we can take its square root, and thus the final expression for W3 will be minus 1/3 plus x square, minus 1/3 plus x square divided by root 2 by 5, 2/3. This square is 2/3 and root 2 by 5 remains in bracket. 2/3 into under root 2 by 5, or that can be written as, see this is at the numerator it will be a reciprocal 3 by 2 root 5 by 2 into minus 1 by 3 plus x square. What we shall do to simplify this as, we can multiply 3 inside the bracket, and this is the root 5 by root 2. So that we multiply by 2 here. So this becomes root 10. We are multiplying by root 2 at numerator and denominator. So divided by 4, you can check it, and we are multiplying by 3 inside the bracket, and that becomes minus 1 plus 3x square. So this is the value of W3. Check it. Yes. And thus we have obtained W1 as 1 by root 2, W2 is this one, and W3 is this, and this is orthonormal set. Thus W1, W2, W3, and which is equal to 1 by root 2 x into root 3 by 2, and this is root 10 by 4 into minus 1 plus 3x square, is orthonormal set, which is basis of this vector space, is an orthonormal set. So we have converted the basis which is a standard basis for a polynomial of vector space of polynomial of degree less than or equal to 1x x square in this form. So now these you can check, these are the vectors which are orthonormal. Each vector will have the length 1, you can check by using this definition, and these are orthonormal to each other. That means this inner product of these two vectors is 0, etc. Pairwise is 0. So is an orthonormal set which is basis of, which forms a basis of or basis for v is equal to f of x. Thus we have converted this basis 1x x square to this basis, and this set is orthonormal set. So this is the process we have used in the proof, or we have stated, we have constructed in the proof of Gram-Schmidt orthogonalization process. And to illustrate that with in terms of example, we have considered these two examples. So please try to understand this. Thank you for watching the lecture.